to input signal. In general, the system will be represented as a block and has input and output. Let's call the input is equal x of t. And the output y of t. And we don't know what inside the system. We are going to assume that the system is linear, time, invariant. Means doesn't change with time. If you have coefficients, will be constant. It's linear. The important property that we're relying on is linear system. What does it mean, linear system? Means if you have input x1, you will have y1. So let's just explain what does it mean, linear system. It's the same system, and if you input x1, the output will be y1. The same system, if you input x2, you will have y2. What about if you have a signal input which is equal the sum of both? Like if you have the same system, I'm talking about the same system, linear, and the input now x is equal to x1 plus x2. What do you expect for the linear system? y1 plus y2. So the output y will be equal y1 plus y2. This is the type of system we are working on today. Now we come for the second problem. How do you know the system? How you figure out the system? There are easy systems you can figure it out. Let's say I have a system like a black box, and you want to know what is the system doing. What you're going to do? Yeah, exactly. You just put input and see what's happening, right? Let me give you an example, and then you call the system. Give me the name of the system. If you have a system like that, and we assume linear, right? And let's say you put a signal, and usually when we test the system, we use the input, specific type of input. What do you think, which input you're going to use? So you can figure out. 0, you get 0. Yes. If you put nothing, you get nothing. Yeah. Just 1. But it's with time now. We are dealing with time. So when you're going to put 1? At specific time, or 1 all the time, or you want to know? Think about it. Just think about it. There's a system and you want to put input. You said, I'm going to put 1 unit, 1 volt, 1 current. Okay, but what is the shape of this system? Straight? I couldn't hear. What do you mean by that? Like continuous like that? Well, if you have it continuous like that, how can you know if the system has delay? You will not feel it, right? So you will feel delay, you need to feel anything else happens to that signal, amplified, delay, anything. So you got to have specific time. Specified. Yeah. Okay, what about if I use impulse? Unit impulse. That will give me everything, right? Like if you have let's say that the input will have unit impulse. So, and at 0. So you can say x of t is equal delta t. That's the input. So let's say you look at the output and see what's happening. Remember, impulse happen at time equal 0. Let's say that you got the output something like that. To delta of t. So what is that?
So it doubled the.
Yes. So the system you can describe as amplifier, right? Amplifier with gain equal to. So this is amplifier. And the gain is equal to. Let's have another system. And let's say that you have the same signal delta t, and the output not amplified, but it happened at time equal to instead of time equal 0. So the output is delta t minus 2. So it's a delay system. That's right. That's delay system. That's a delay element, yeah. And so on. But I give you in the beginning easy system so we can understand how you can test the system. So that's a delay system. That's amplified. But what we did, we input a unit impulse. A unit impulse. So any system can be described by the unit impulse response. Any system, and we call it h of t. So when you say h of t, for example, for this system, you put x of t. If you put x of t, you get y of t delayed by 2. So in this case, this system h of t describe the system, and I can find the output of any other signal. What do I mean by this? It means if you don't input, let's look, now talk about the delay system. Let's say that the input was something different like that. That's a delay system. And the input was something different. Let's say triangular wave, or from 0 to 2, and the height is equal to, that's x of t. So you can describe it as x of t is equal to, how you describe this? That's like a straight line with the slope equal 1 t. And it's from t greater than or equal 0, less than 2, and 0 otherwise. You agree with me about the description of this function? So what do you think about the output look like for this system? Let me make it clear. This is the same system that we described last time, delay system. That's the delay system I'm using. So what is the output? Will be shifted or delayed by 2 units. Exactly right. It will do the same thing already because I tested. I know what is happening. So that's 0, 1, 2. So from 2 to 4, nothing happened to the amplitude. That will be y of t. So y of t will be equal to, now what is the equation of this function? Not if you, well, let's just try here. We'll say y is equal t plus some kind of c, but it's equal 0 at 2. So y is equal 0 when t equal 2 plus c. So what's the value of c? Negative 2. So you can say it's equal t negative 2 when t greater than 2, less than 4, and 0 otherwise. So the system has a delay. Okay. Yes.
In most cases, the shift is just a time delay.
It depends on the type of shift. Delay when it's shifted towards the right. Advance if it's shifted towards the left.
How many units it's been shifted before we see YFT?
By the test we did by unit step. I'm sorry, by the unit impulse. So the impulse response H of t, it's the guide that to tell you impulse response. So to figure out the output of any signal, first you got to have the impulse response of the system. But of course, I started with easy systems. Sometimes you have system does everything, does amplification, delay, and other things. So let's see another example. And I want to think about it. That's a linear time invariant system. Generate a unit rectangular pulse of width 3 when a unit impulse is applied to the system. Find the impulse response of the system. Find the response of the system when the input is equal delta t plus delta t minus 2. That's one simple application for what we did. Let's just see how we'll do that. I want you to help me solve this problem. Can you see it? So let's figure out how to solve part A. The system generates a unit rectangular pulse of width 3 when a unit impulse is applied to the system. So when you have a system like that, let's just make it to the box. And he said that if you have input unit of course to be at 0, the output would be rectangular pulse of width 3. We did that in the elementary signal, if you remember. The normal rectangular or unit rectangular pulse, it's a rectangle and it's symmetric about the y-axis at x equals 0. It's in the middle, the y-axis in the middle. So if this is 0, that would be the rectangle. And the width is equal 3. The whole width is equal 3. So what does it mean? Start from what time to what time? Negative 1.5, that's right, negative 1.5 to negative 1.5 to positive 1.5, and this one in the middle. And the height is equal 1 because it's normal or unit rectangular pulse. That's the output for unit. So now we'll figure out the system. That's given. I'm just graphing what this is. Generate a unit rectangle pulse. That's a rectangle, and it's unity means the height is equal 1. Width is equal 3. That's the width equal 3. All right. And that's what. So A, find impulse response of the system. We did it. And if you like to express it mathematically, it's easy. That's x of t equal delta of t at 0. And that's y of t. I got to write equation for it. It's not easy, just y of t
it's equal 1 when t greater than negative 1.5 and less than 1.5 and equal 0 elsewhere. All right, we understand that. Now let's look for the part B. Part B said that the input x of t is equal to delta t plus delta t minus 2. So how to solve something like that? The input is equal to the sum of two inputs, and we have linear system. So what should you do? Yeah, I just don't hear somebody. Yeah.
You add them together.
Yes, exactly. You get the response of each one separately and then add them together. Why we are adding them? Because linear system have the superposition property. So let's do that. So the first one, delta t, we agree about that's going to give us a rectangle. And it's from minus 1.5 to 1.5 and 0 here in the middle, and the height is equal 1. Now we want to get the response for delta t minus 2. So what the response you think? Shifted to the right, exactly, because the input was shifted. So we just do that. That's the time axis, and shifted by 2. So 0 here will be the pulse will be in this direction, shifted by 2, right? So the axis of the rectangular pulse at 0. So and the axis of the rectangular pulse for the second one, it will be at 2, right? That's fair. Yeah, this one was at 0, this one at 2. And then I will sketch the rectangle. The width is equal 3. So I'll just do exactly the same width as we did in the top one. And what about the, it's always negative 1.5, 1.5. I'm taking each unit in the x-axis or time axis 1.5. So that's 2. So you subtract 1.5 from 2, what you get? 0.5, right? So that's, you have exactly right. That's 0.5. And you add 1.5, so you got 3.5. So that's y1 and that's y2. So the total response, I'm going to add both of them. So let's just take it here. I will start from negative 1.5. You look for the least one to the left here. You have negative 1.5. At t equal negative 1.5, the response is equal 1 up to 0.5, right? By the way, I didn't sketch it in the right scale because I'd like to make it in, if I'm saying that's 1.5, let me make it because I'm making this negative 1.5, I'm trying to, because I'm going to add in graphic, it should be correct. So I'm going to sketch it in the right scale. If this is 1, I will make h11, so 0, that's 1, that's 1.5. That's negative 1, that's negative 1.5. That's 1.5, and that's the height is equal 1. It's okay to take it. And that's y1. And that's the 0. So if this is the 0, I make shift 2. We said that will be 0.5. And I'd like to make a line from 0.5 up to here. And I have 2, 3, 3.5. I make a line just to know when I'm adding. And that's the response. So I have response here just to make you understand. That's the output Y2, and that's the output Y1. Now I'm adding. Now it's clear. From negative 1.5, that's the 0, and that's negative 1.5. The same line here. It's equal 1, right? It continue 1 up to 0.5. You see, up to 0.5. So that's the 0.5, and that's negative 1.5. The output will be 1. Okay, that's 1. From 0.5, this point, 0.5. From 0.5, this point, up to 1.5, you have 1, and you have 1 here, right? So 1 plus 1 is equal 2, and that's up to 1.5. So that's 1, 1.5, 1.5, that would be 2. And from 1.5 up to 3, that's 3.5. It will go back again to 1. Exactly. When they intersect, it's equal to, that's right. Let me just make it clear here. Because adding and then. So that will be the output. So you can get the output using the superposition. I did for you that for the notes or I'm going to publish in the Fourier system. I made like simple exercise for you. Yes. Because when you are adding in the middle, it's between, if you know this point is 0.5, the time is 0.5. At 0.5, after 0.5, it's equal 1 here. And in the second response, after the time equal 0.5, the response is equal 1. And this continue up to this point, which is equal 1.5 for the first signal. So from 0.5 to minus 1.5 during this period, you will find both signals are equal 1. So when you are adding them, you're getting 2. But after you exceed 1.5, Y1 go back again to 0, but Y2 still having 1 as amplitude. So when you add 0 and 1, you get 1 again. So that's how you get both of them. Of course, that can be described mathematically also. When you do the math, you can add them, but graphically, it's very obvious you can see it. So you are going to have like checkpoint 1. I'll give you some similar example that will make you understand. So the point is clear. Now we'll go for the important part. We did simple signal, like impulse. We did simple response. You're getting rectangle as an output. But what about in general system? If you have the input not sum of impulses, if you have the input, let's say exponential function, or you have unit step, you have something expressed as a function of time, that would be hard to do. Yes, you can do graphically, but it's hard to calculate it. I add 1 and 1, or this is 1. But when you're talking about exponential e power minus alpha t or something like that, you cannot find, you have to find the value at each point, right? And you add it. But mathematically, you are not going to add it. You are going to integrate it. when you have two things. Okay. So there is a method called convolution integral that will help mathematically and graphically to figure out the response of a linear time system. And I have example here that will work out together. And the same system I'm going to explain here, you will find in the note published in the folio system, has also how to do it using MATLAB simulation. So you'll be prepared for next lab. Let's say that you have a system and you know the unit impulse, or you know the impulse response, and you know the input, and you want to find the out. So how we'll do it? We write it like that. We say y of t is equal the input convoluted on the pulse response. This star does not mean multiplication. It means convolution. So we'll say x of t is convoluted with h of t. H of t, that's the impulse response. And x of t, that's the input signal. And y of t, it's the output signal. The question is, how can we find this output? Or what does it mean convolution with continuous time signal? How we do the integral? Okay. I will write for you the integral form of the convolution. We just wrote here now. Y of t is equal to the integration from negative infinity to infinity, x of t minus tau, h tau, d tau. So we're integrating with respect to tau, that's dummy variable, and t will be constant. We can do it in different way, because y of t, as we said, x convoluted on h, it's the same as h of t convoluted with x. If you exchange it, you get the same result. But you can express it with different integration now, say negative infinity to infinity. And instead of saying xt minus tau, you can write ht minus tau. Instead of h tau, it will be x tau. You will get the same result. You can use either expression, and I will tell you when you can use it. Of course, you can use both. In any situation, you'll get the same result. But there are some advice about when you use the first or the second. To do this integration, I'm not going just to do integration. I'll get you function, substitute. It will be easy to do. No, I want you to understand the process graphically. But before I start, I want to check if you still remember from the basic operation on signals, how can you find something like that? Because originally the signals are given in time domain t, small. Now we are expressing everything in tau. So how you sketch this? How you do that? Because it would be like kind of our brain used to something, and now we are changing from t to tau, then we'll be confused. Let me explain what does it mean in one example. Let's say that you have a function like that. rectangle function, and that's the time domain. And that's the vertical axis. And let me call it h of t. That's originally given everything in time. That's 0, and that's 1, and that's 1. That's h of time. I want to sketch h of t minus tau. Because I'm going to change the variables from t to tau. So now t, I am not going to consider it as a variable. No, I have a new variable called tau. Tau is going to express for me the general time, and the small letter t will be a fixed number. Could be 1, 2, 3, minus 4. I'm going to do that. So to do that, the first thing I have to express h of t, h of tau. So what you'll do, it'll be easy. Just all what's supposed to do, exchange from t, write tau. And that will be h of tau. And you do the same thing. Nothing actually changed. Just I changed the name. Tau, tau, that's it. But now, let's try to train your brain. Tau is the variable, not t. Small t now is like constant. Like, for example, you can say t equal 2. Because I want to, why I'm doing that? Because I'll make tau as variable, and then we ask, what is the response of the system at t equal 2? So it will be constant. I want to find the response of the system at t equal minus 3. So now I'm dealing with t, small t, as a constant. And that's why I change it. I make tau. First of all, how I make h? Okay, let me just write like that. How you do that? 2 minus tau. Keep in your mind, tau is the variable. We did that before in the basic operation of segments. But let me refresh your memory now. Go back, because our brain really, it's you got to train your brain how we can change names, and then you'll be fine. If I ask the problem in this way, can you do that? You tell me yes. It's shift towards the left by -2, right? What about that? To do that, there are many ways. If you remember, you can make first the shift and make the inversion after that. True? Another way, you can take minus as a common factor, t minus 2, and what you're going to do? Yes. You make the inversion. When you do that, you make the inversion first, and then you shift it to the right by 2. That's right. What about if you do that? H minus t minus 2. You will say h minus t plus 2. So what you'll do? Inversion first, and then. So if I was dealing with the same function, I did just 1 and 1, just to give you. If I'm working with t, not tau. Just I'm just trying to review. And let's say that you want to make h 2 minus t. If you want to do that, how you'll do it? You will say it means h minus t plus 2. It means h minus, and then you have t minus 2. I'm doing the second approach. I will make the inversion first, then I will do the shift. So if you make the inversion first of this one, it means that you're going to do that. This one will be flipped as a mirror. So 1 will be -1, and this is still the same. You will get this. What is that? That's h of minus t. Now, because I take the negative out common factor, because I'm using the second approach. So t minus 2. Minus 2 means I'm going to shift it towards the right by 2. So if I do that, so I have it 1, it becomes 0, and then 2. So it means it will be here. Because when you add -1 plus 2, you get +1. So that,
Wouldn't it start at 1 and then go to 2?
oh, yeah, right, yeah. Because I'm making this point. You are right. Yes, that's fine. Oh, we can erase this. Okay, it's easy. So from 1 actually starting, yeah, because I'm moving this point. You are right. So that would from 1 to 2, and you have the triangle. That will be h minus t plus 2 that I simplified it. That's h minus t plus 2. So if you look at the front, let me just color this one because I want to say something here. So that was the original. So what's happened? When you have h2 minus t, I inverted. So that's the inversion. Well, that's h minus t. And then 2, because 2 is positive, I moved in the front by 2. Because the distance between this point and this point is 2, right? Why I did that on t? So when we go back to the problem here, I want to do now h2 minus tau. And now I'm dealing with tau. Let me sketch feedback again. That's the original signal. But now I'm using tau, and that's h tau, and that's 1, and that's 1. So when I say h t minus tau, keep in your mind t numbers could be 1, 2, 3, 4, whatever. But the important thing, you should sketch h minus 2, which should be like that. And you keep in your mind, since you have t here in the front, so you are moving toward the right by t, if it's positive, of course. If t equal 1, if t equals 0, you are not moving. You are at h minus tau. If you say I want to find ht minus tau at t equal 1, means I'm moving 1 unit towards the right, right? h2 minus tau, I'm moving 2. So now I want just to keep it, because this will continue in every single problem will have t minus tau. So that's why I want to make it for you easy now. Train your brain, you will flip and then move towards the right. When t is positive mark. All right. And most of the time we're going to, all right, that's good. Now we'll go to the problem that we want to solve. You have h of t that I already give it to you. I'll work a little bit on it. That's h of t. And the input to the system is a rectangular and of width equal to and shifted. So that's x of t. The height of the signal is 1. That's 1, that's 2. And that's h of t, and that's t. Remember, what's h of t? What's h of t? Impulse response. This is a system when there's impulse. Think about it. I will go back to the example I saw so you will understand what I'm saying. Why am I flipping the functions? When we have this problem we will solve. when we have something like that, delta t minus 2, everything was shifted. Why? Because when you do something like that, it means at time equals 0. I just want to make it easy for you to understand. Let's say that you have something like that going to the system. That's height 1, 2, 3, going to any system. And the system, for example, exponential, let's say exponential, or whatever. What does it mean? When this signal input to the system, we think that this signal, it is the first one going to the system. Right? You think that because this is the closer, so you think the signal is going in. So this pulse of height 3 going in first, and then the height 2 and height 1. No, it's not. It looks like going in this direction, but you have to look at the time. This happened at 2 seconds, after 2 seconds. So the first one will go this one, because this at time equals 0. And after 1 second, this one will go with height 2. So that's why we flip the signal. Because when we sketch it, the time axis, we make our 0 from the left. So I want to make it in other direction. That's why. And that's why we say, okay, you got to flip one axis. You flip h of t axis or you flip x of t. So do you understand now why we make reflection? We make it minus tau because of this reason. Because when we sketch it, it's just our 0 from the left and increasing in this direction. So why I'm telling you that? Because I had this class when I was a student, and I don't know how they are flipping the signal. Ask your friends, whoever take the course, or in any university. I did the same thing. I don't know why they are flipping the signal. Why making h minus tau? I didn't know why. They do it. I did. I knew how to solve it. I did. I flip it, and sometimes when you're a student, some method, maybe you don't understand why, but you do it, right? I hate this when I was a student, and I got to know why. So I spent the whole semester, and I'm flipping the signal, adding t. I don't know why, and I'm getting the right answer, no problem. But I don't know why they flip. Till when I go, that's after I finished by 1 year, and then I was doing experiments, and I have pulses, was like discrete, and I was recording everything. Then I found that the pulse going, it was 1. I said, that makes sense. That's true. So that's the whole reason of that. So now let's work with this problem, and we're going to flip h of t. But before that, you got to change the variable from t to tau, and that's easy. On the same axis, what you're going to do, you do that. Just erase t and make it tau. You don't have to sketch it again. That's the first thing. 0, 1, 1. Remember when I told you that you got to flip one and you leave the other? Let me make myself clear. I give you two formula here. It's either xt minus tau times h of tau or h of t. So there's one you flip it and one you leave it as it is. So it's either you flip x or you flip h. And I told you both they work right. If you choose any one for any problem, both will give you the right result. But I'll tell you about when my experience when I'm solving this problem, I found it's easier to flip the shorter period, the one that has shorter period. Like this x of t, it's there from 0 to 2, and the rest zeros. But this one, it's only from 0 to 1. So the period where the signal exists, short period of time. This one you flip. If tau was the opposite, you flip. So it doesn't matter which one. So I'm going to flip h of tau. And since I'm going to, whoever you're going to flip, now change the order. What does it mean? The signal you're going to flip, put it to the left, and the one will be fixed, leave it at the right. In one axis now, in one graph, I'm sorry. So that's the graph. And now you pay attention for what's coming. because we're going to integrate in a way. It has a deep thinking. I mean, this is a simple, but it has really deep thinking. The people that they think about how to find the response. I mean, they spend, I think, a long time to figure it out. So that's the time. And I'm going to keep x of tau as it is. So it's from 0 to 2. From 0 to 2. All right. And height is 1. And now I'm going to flip h of tau. How I flip h of tau? It's easy, just to make it like that. It'll be from -1 and height is 1. And we are going to color it. So that's h of tau minus tau, and that's x of tau. Now I want to add t to negative tau for h. We said that when you add t, positive number, it means you are moving the whole thing towards the right, right? What's happening now? I'm trying to find when this signal, h of negative tau, when I move it to the right, when it will overlap with x of tau. Keep it in your mind. You will never get output if there is no overlap. You have to interact. The input has to be inside the system, right? So this signal, it starts to move toward the right, but till now, the t is equal 0, right? Because we want to express h t minus tau when t equals 0 or negative. Because what happens if t negative? Where this triangle will be? Will be far away to the left. No interaction with the system, no overlap. So when there is no overlap, the output is equal 0. So we'll say that when t less than or equal 0, no overlap. As you see from this picture, this one is at t equals 0. No overlap. It means y is equal to 0. Now I will start to move the triangle inside this rectangle. I will take the same. Okay. Yes, your question?
Is that a 0 next to the y equals?
Yes, it is 0. Yeah. Let's take a copy of this one. Okay. Now I'm going to move this triangle inside. So the first thing, that's x of t. It was here, so I move it a little bit. T. What do you mean by t? Well, you go back here. At this, if I'm talking about this triangle, this edge in the front here, that's at t equals 0. If you move it 1 second, 2 seconds, 3 seconds, I move it by t, right? Right. We'll do that. That's t. And what about that? Let me go back. That was 0. The t was 0, and this one -1. It's the end of the signal far by 1. So if this is t, so what is the value of this point? T minus 1. Right? Because when t equals 0, that was -1. So it's always, you subtract 1. Let me show you again. That was 0 in the front of the signal 0. The tail is -1. So always -1. So if you put t equal 2, for example, you will have 1. You put t equal 1, this one will be 1 minus will be 0, and so on. So there is overlap. You are going to investigate stage by stage. The first one, no overlap. The second one, there is overlap. But don't move because I choose this signal, which was shorter interval. I choose it intentionally. So I know at one moment, all the signal will be inside, be completely inside an overlap, right? I'm not doing that now. I'm doing just partial overlap. Partial overlap, valid from what interval? In other words, t should not exceed what? Another way, when this signal completely inside, the first instant, when t equal 1 or 2?
It should be less than or equal to 1. Less than.
Okay, I'm talking about this t, right?
Yeah.
Should be?
It has to be greater than.
Greater than 1? Greater than 1 would be like 1.5. Remember, the interval is equal 1. Like, the best thing to answer this question, just this is t, this t minus 1. So now I want somebody to give me an answer. What the value of t you expect? 1. All right. If you put 1 here, so 1 minus 1 is equal. That's right. It will be just all of it inside. Whoever said 2, if you put t equal 2, so t minus 1 will be 2 minus 1 be 1 will be completely inside. So it's completely. But you want it in the edge. So when the tail comes at 0, it means you want it like that. Just let me sketch. If this is the input, you want the signal to go. That's 1. That's 2. This is the end of the partial. I started from 0, and I'm moving, sliding the signal step by step till it's completely just on the edge inside. So the time will be from 0 to 1. Start from 0 to 1, you will have partial. It should be greater than 0 and less than 1, right? So for t greater than 0, less than 1, we have partial overlap. Right? You agree? Well. Yes. Because if you put t equal to this end, t minus 1 will be 2 minus 1 is equal 1. So it will be something like that. It will be that's x, and the h will be from 1 to 2. You are here. You don't want this situation. You are completely inside. No, you want to be in the edge, just in the edge. You shouldn't get even to 0. That's what I'm saying. T greater than 0 and less than 1. Less than 1. Because at 1, it starts the complete overlap. So from 0 to 1. From 0, you should exceed 0, because 0 is still outside. And 1 will be just, in this case, just starting the complete overlap. But if you choose t equal 2, you are here. You moved a lot. You are already inside the overlap. You pass by many stages. You won't take stages. So why you are making stages? Because you're going to integrate. Now, how you integrate this? Remember the integration that we did it? Y of t equal the integration from -infinity to infinity. H t minus tau x tau del tau. I'm using the second one. When now you do the integration, you integrate from where to where? The overlap starts from what time? 0 up to t. No, t is variable because you have to put it in imagination. At point 1, it's a case. It's in the same case. 0.01, 0.02, 0.0. It's up to when t equal 1. So you want to make the integration see the general expression. So you will say that the integration will be from not from negative infinity, from 0 up to t. You got to remember t is a constant, but it has many values. For example, if you are asked to find the response when t equal 0.5, you make the integration, and in the end, in the expression, you put t equal 0.5. When we ask about find the response when t is equal 0.9, make this integration function of t, and then put. When I ask you find the response at t equal 1.5, this expression I'm doing right now will not work for it, because 1.5 exceed 1. That's for complete overlap. You don't do it. Do the only partial. It's t minus tau. How we get the expression for h t minus tau? Very simple. You go back to the h of t. That's h of t, right? Write the equation of h of t. Do you know how to write the equation of h of t? Okay. H of t equal to what? The slope of this straight line in negative, so negative t plus 1, that's right. Okay. I'm asking for expression ht minus tau. So what you're supposed to do? If you have h of t, I ask to find h of 4. What you'll do? You substitute by t equal 4. H of 10, h of t minus tau. Substitute t by t minus tau. Minus t minus tau plus 1 will be equal minus t plus tau plus 1. That will be the expression. Minus t plus tau plus 1. So that's how you get it. Very simple. Just go to the equation and substitute. So we will have minus t plus tau plus 1. We found it. What about x of tau? It's easy. It's equal 1, right? It's 1. The integration with respect tau. Now look for the integration. By the way, I'm going to do it like that. 0 t minus t plus 1. I put it in one bracket. And plus tau in another integration. Why I'm doing that? Because I want you to remember tau is the variable, t is a constant. And that's why I am breaking t from 0 to t. And t is constant with respect to tau. So you leave tau by itself, and the rest of the numbers keep him, not to confuse yourself. Because I'm afraid to make integration, because we are used to, our brain used to, the integration of t squared over 2. No, t is constant with respect to tau. So what is the integration of a constant? When I ask you the integration of 5, what are you going to say? 5 tau, right? So that constant, get it outside, negative t plus 1 tau, and the limit from 0 to t. The integration of tau with respect to tau. Tau squared over 2. So I did the integration, and the result will be like that. T minus 0.5 t squared. That's y of t. And you got to remember this output only valid for t greater than 0, less than 1. important to find the values at the boundary of the limit of the time. Very important. And I'll tell you why. Because this will prove that if you are working right or wrong. Because you have many stages. And when you finish one stage, you start a new stage, the end of a stage should be equal to the beginning of other stage. If they are not equal, it means there's a mistake in my calculation. That's the one that can. So let's find the value of y at 0. What do you expect? When t equals 0, did you find the output? Yes, we did. At t equals 0, the first one, when there is no overlap, was 0, right? So now when you put t equals 0, the new expression should be equal 0. You got 0? Yes. Yes. 0 minus 1, 0. What about y1? v1 minus 0.5 times 1 squared. I'm substituting this expression. Will be equal 1 minus 0.5 will be equal 0.5. Keep this in your mind. That's, I will just make it in a box. And y of 1 is equal 0.5. That's important. All right. Let's go and see what's happening. It will move to be completely n, right? All right. That's the second stage. It's moving, 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 and then start to be n, and now all the pulse is n. Let me just do it in this. And that's 2, 0. It's still t minus 1. It just do it one time. You know what's the beginning and the end? That's one time. It keep with you because t can be any number. That's tau. You make it clear that it's tau. This is tau, not time. Now this is 1. Now it's completely n. So the first thing we do, we move the graph. Second thing, we'll find the interval of time that's valid for each stage. Just the stage before that, partial overlapping, we just said the t should be greater than 1, greater than 0, less than 1. What about this? What's your limit? When you want to find the limit, say, I want in this case, it's moving in overlapping. You don't want to get out of the square, right? So what's the limit in t? 2? Well, let me just sketch. That's 2. It means t equal 2. It means it will be like that, right? If it move a little bit after that, what will happen? So that's right. So t should not exceed 2, right? All right. So say t less than 2. Bigger than what? Exactly 1, because the last stage was finished at 1. The last stage from 0 to 1. So this moved from 1 to. If this square was bigger, 3. The width was 3 seconds. So your condition will be t greater than 1 less than 3. Right? Yeah. Now, so we follow the step, we sketch it, we find the time limit for it. Then what we're supposed to do? Integrate. How integrate? The same expression that we did still valid with you, right? Because this is the h t minus tau. It's fixed. So I'll go for the integration I did before. All these steps, the same, but I have to be careful about the limit. So let us write the limit of integration. The limit of integration from what to what?
Minus 1 to t.
Not minus 1. It's obvious here. Yeah. 0, 0, 0. I mean, just look for overlap. The overlap area it's shaded. From t minus 1, that's right. From t minus 1, t, this is the shaded area. Look at the previous one. The previous one was from 0, because before 0, there's no overlap. Start from 0 up to t. So this from t minus 1 up to t, the same integration. So I advise you, don't make the integration. Take the result, it change the limit. That's all. So, but I have to write the expression so when you review, no. So I will write the same thing. You don't have to do it twice, it's only one time. And I will take the result. I'll take the result. Just let me show you how I will take the result here. And I'll just change the limit. I have from t minus 1 up to t, from t minus 1 up to t. And I calculated, I found that's equal to 0.5, not a function of time, constant. 0.5. When it's moving, and that means, you know what? Because this area is fixed. When it's moving, it's completely inside overlapping, and this area is moving. The area does not change, right? The same. Okay. So be 0.5 up to now. Let me just refresh me what we did to that. First, no overlap. No overlap. Then we have entry partial overlapping. Then we have complete overlapping. And now exit partial overlap. Because when we start to get out, still some part in. So we have overlap, partial overlap, but this is our way out, exit. So how we sketch it? Let me sketch for you. And you found the limit. That's the square. And partial, let's say here. This is the only part overlap in our way out. Well, that's fixed, 0, that's 2. What about that? Never change, that's t. What about that? T minus 1. The limit. T, you know t should be greater than what? You go for the last one, it was end at 2, should be greater than 2. But less than what? When this one will be on the edge out completely. When this will happen? It will happen when the triangle becomes like that, right? So t will be here, right? That will be at 3, right? So t greater than 2, less than 3. Because once you get 3, completely exit out, no overlap. So now I want to do the integration for this one. The integration now will be the same, but the limit from t minus 1 up to 2. Why? Because the area where there is no overlapping is 0. Because I mean, you multiply and integrate. So 0 by something is 0. What do you mean 0? Because the x of tau, it's 1 up to 2, then after this is 0. So multiply 0 by something, it's 0. So you integrate from t negative 1 up to 2. This. Don't do integration. Take the result of the integration and use this, the limit from t minus 1 to 2. I'll give you the result from 2 to 3. I got 3 minus t square over 2. I have to write again clear. Y of t equal to 3 minus t square over 2. That's for t greater than 2, less than 3. And as we said before, there's a check. The endpoints 2 and 3, especially 2. Y2 will be equal to 3 minus 2 square divided by 2. 3 minus 2 is equal 1. Square over 2 is equal 0.5. It was 0.5. Now I have y of 3 I will have 3 minus 3 over 2, 0. And that's expected because it will be completely no overlap. No overlap. It will be 0 after that. So what in the end we're going to do? You calculate the order response, sketch it. So I will sketch now the y. And you remember, we did, that's y of t. We said before y of t is equal 0. That's 0. And our refresh your memory, we did from after 0, from 0 to 1, what the result? From 0 to 1. From 0 to 1, that's what we got. T minus 0.5 t squared. T minus 0.5 t squared. If you put 0, 0, if you put t equal t minus 0.5 t squared, you put 0, and you put t equal to 1, 1 minus 1 minus 0.5, 0.5 will be something like that. To reach 0.5, then 0.5 up to 2, and from 2 to 3 will be back again to 0. That will be the response, y of t. So if you want to find the output at any time, for example, if I ask you, what is the response when t equal 1.5 from the graph? 0.5. When I ask about the response at 0.5, you go to the equation, substitute for this one. If you want to at 2.5, you go for this equation and substitute. You have the graph, you have the function of each one. Any question? With this, you cannot understand by yourself in the house. You can't. When you go home, you go study. So if you don't understand something, you get to tell. Right? Okay. Check yourself with the checkpoint. I have exercise here and try to do it. Okay.